Along the ledge of this beautiful precipice, traffic moves at unreduced rates of speed. Safe distance between cars is maintained by automatic radio control. Curved sides assist the driver in keeping his car within the proper lane under all circumstances.
Well done, Firebird 2. You're now under automatic control. Hands-off steering.
Fully automatic highways. No need for driver to touch steering wheel or accelerator or brakes. A full-time electronic chauffeur service for expressways and limited access roads. Here in Washington, D.C., some of the nation's leading traffic engineers, highway safety experts, and government officials welcome the opportunity to inspect this potential solution to problems of highway safety.
Wire guidance engaged.
The Stanford Racing Team tries to win the Dark Grand Challenge. It's a collection of about 50 people from various companies like Davidoff, Volkswagen of America and Stanford University. And we built a car that is driven by some of the most advanced artificial intelligence currently on the market. What you see here is our car Stanley. It's a off-the-shelf Touareg, just slightly modified to be strong enough for the race. It has a bumper in the front, it has skid plating underneath. And that's pretty much it. So it's basically a off-the-shelf Volkswagen Touareg. We've equipped it with all kinds of sensors on the roof. You see a laser system. A laser system allows us to scan the terrain ahead of the vehicle in 3D, just like a video game. At the center, very hard to see, you see a conventional camera. It works just like a television camera that's being used to produce television images. And then we have a radar system that can see things like parked vehicles 200 meters out, so quite a range. Inside the vehicle itself, we've modified it a little bit to make it drivable by a computer. The Touareg is natively throttle and brake by wire, which means you just have to hack yourself into the Touareg to make it accelerate and decelerate. But for the steering itself, we have a little motor down here that attaches to the steering column and that really, really quickly can actuate the steering wheel. The most important thing of the car, however, is its brain. This is all about intelligence. It's about making a machine smarter, not stronger. So this is how in 2005 car brains look like. They'll be much smaller in the future. It's a rack of 6 computers, essentially Pentium M, like laptop type computers down here. On top of it, we have a box where we can reset all the physical components, the sensors in software. So if a sensor fails, we can power cycle it. And then we have various small components. We have a power system over here, an emergency e-stop system required by the organizers of the race. We have an interface to the car itself over here. We have a GPS unit over here, and we have a power inverter over here. All this stuff works together. It runs all kinds of artificial intelligence algorithms for the control of the car. I can't show you the algorithms because they're inside the computer, but trust me, they have a really good chance to win at race day.
The Stanford Racing Team's Stanley is a fully functional, autonomous vehicle capable of perception, path planning, and control at high speed. Months ahead of the challenge, Stanley has already logged more than 100 autonomous miles in challenging terrain and exhibits many promising racing qualities. Stanley can drive autonomously at 35 miles per hour, avoid obstacles at high speeds, and effortlessly survive the natural hazards of an off-road course. Stanley's low-level throttle and brake control are natively by wire. Steering is actuated by a motorized chain drive attached to the steering column.
On the right, a magnet cylinder can be seen, as on the left, a magnetometer can measure magnetic fields. Magnet should be buried in the center of lanes.
Okay, you guys, could you clear the track so we can go by? Thank you.
By the way, don't you have to worry about the speed not coming.
Now I switch on the steering, the brakes, And the throttle?
Chen, can you check on this lateral code? When you stop, let me know.
In the market to buy a new car?
What options do you want?
I think I know to stop right now.
They've come up with a new option, one that leaves the driving to the car.
The National Automated Highway System Consortium brings hope. NAHSC is a diverse team of companies, government, and universities at the helm of a breakthrough in transportation technology. The challenge? To plan the system so the technology saves lives, time, money, and the environment. The consortium participants are showing how it can be done at Demo 97.
Demo 97 is a congressionally mandated proof of technical feasibility demonstration. Really, it's our chance to show the world what intelligent vehicles and highways are all about, and it'll happen this August in San Diego.
Put the key in, but yeah, here we are. Both Dean and I are driving with no hands. We're coming up to this obstacle up here, but this is pretty cool. I wonder what the other traffic thinks. All right, it sees the barrels and is swerving. And we're around it. No hands.
The consortium calls them scenarios. These scenarios demonstrate the technical feasibility of various types of automated highway technologies and how they will increase safety and decrease traffic congestion.
We'll be showing platoons of vehicles. That's several vehicles spaced closely together. That'll show us some increased capacity options on the highway. We'll be showing a free agent scenario where we have an automated vehicle mixed with manual traffic. That shows how we could incrementally deploy these vehicles in the very near term. We'll also be showing transit vehicles, buses, how they can be automated, along with a number of other features and functions of an automated highway.
For example, the technology the consortium is demonstrating includes adaptive cruise control, which senses vehicles ahead and alters speeds accordingly. This is done through the use of different types of sensors. Collision avoidance, which detects obstacles and other vehicles in the road and safely adjusts the course for a single vehicle or a platoon. Cars can communicate driving information through a combination of sensors and communication signals. And lane-keeping technologies using video cameras or markers that are tracked by magnetic sensors in a vehicle, ensuring lanes are followed precisely. The vehicle can then calculate its exact location in relation to data it rapidly reads.
William